Okay, good. So, good morning, everyone. My name is Denis, and today I will be talking about a recent project of us. Uh, okay. Can you hear me now? Okay. So, the title of my. Let me just. What is the pointer here? Okay. Okay. Okay, thanks. So, today I'll be talking about protected helicoid states in non-cylindrical, in non-topological cylindrical quantum dots. So, this work was done with Carlos Egas, my advisor, former advisor from the University of São Paulo, and in collaboration with Michael Flatte from the University of Iowa. So the outline of my talk will be, I will be talking about some introduction concerning these two topological insulator in two dimension, just give a brief introduction about what is new in this kind of material. So then I will talk about the results of my work, that it's basically results on the quantum dot matter structures. And then I will show some further calculations that we have to finish. So what is a topological insulator? Well, topological insulator in two dimensions, it's a insulator in two dimensions, as the name already said. So it is a gapped system in 2D. However, topological insulator have the different property that when we make a confinement with vacuum, for instance, some metallic add states will appear on the interface. So this is why we call them metallic add states. So these metallic add states have the interesting property of being helical add states, which means that the momentum it's locked to the spin. So in other words, spin up, spin down electron just go to positive x direction, and spin up just go to negative x direction. So what about the topological word? What does it mean in this context? Well, topological here means that no matter how you deform the edge of your sample, no matter how you deform, adiabatically deform the bands, valence and the conduction bands of your system, if you do not close the gap, or if you do not break time reversal symmetry, you always will find the helical add states inside the gap. So more formally speaking, there is a proposal from Kano where you can calculate in this topological number that in principle does not depend on geometry of your confinement, neither the geometry of your bands. If you do not close the gap, or if you do not break time reversal symmetry, you always will find the same topological invariant. So in the sense, it doesn't depend on geometry of your system, it just depends on the topology of your system. So now we can ask, what is the difference between a piece of rubber with a metal on the surface compared to a topological insulator? Is there any kind of difference? Well, actually, the answer is yes. If we think in electrons in the surface of a metal, each time that an electron finds an impurity, there is a probability of it to be transmitted through this impurity and a probability to be reflected. This probability to be reflected, it's what gives to us the macroscopic resistance in metals. So now we can ask the same question to topological insulators. What happens when with some electron we spin up, for instance, finds an impurity in this 2D topological insulator? Can this electron come back, leading to some kind of backscattering? Well, we can see that if you have our firm energy in the gap, the only way to come back is by flipping the spin. So if you have elastic scattering with no magnetic impurity, we can show with the time reversal time reversal symmetry, more precisely due to the anti-unitary property of the time reversal symmetry, we show that it's impossible to have the backscattering. So in topological insulator, when we are talking about electric scattering, every time that an electron finds an impurity, it never goes back. So they just go through on this impurity. So this is what those guys say that is the metallic dissipationless metallic states. So in this sense, the electrons traveling inside this topological insulator material, they do not lead to dissipation. So here I will just use some analogy by choosing. So a good way to understand this, what happens inside this material, is by comparing the electrons in a metal. They correspond to the crazy traffic in India. So different direction to go, a mess, you can go back and forth in the same street, it's crazy. So what about topological insulator? Well, topological insulator are more like highway. So if you want to go to north, let's say, you have to be on the right side of the road. And if you want to go to south, you have to be on the left side of the road. And sure that here, the right side just can have it spin up, and the left side just can have it spin down. So, however, there's an additional point in this analogy that electron in topological insulator never stop in an eventual hit car. So he just go through on it. So now I show my results. So here we choose to work with a quantum dot. That is basically a material which is confined in X, Y, and Z direction. So quantum dots are like artificial atoms. They have discretized energy levels that in function of some quantum number. So here I will first show the results for mercury telluride. So here it's the subbands of the mercury telluride when I confine in Z direction, for instance. So we see that there is a crossing of this subband in the sense that we have a topological phase transition. So for thickness D less than critical thickness 3.3, I have a normal insulator with a gap. And for thickness greater than critical thickness 3.3 nanometers, I have a topological insulator. So exactly. It's just the subbands of my quantum well. So to find the energy and the wave function and current of my system, I will be using the BET model, first introduced by Bernevig, the famous science paper of 2006. And I will add a confinement cylindrical potential given by this form. So basically, this is the profile of my ether structure. So the first result that I show, it's, okay, so I don't want to spend much time on this, but the beauty of this work is that we can find the transital equation for all the energies of our system. So we just need to plug in the Z component of the total angular momentum in this equation. We can solve and we can find all the energy for each Z component of the total angular momentum. So once you find this energy, we just have to plug in here, and we have an analytical closed form for the wave function. We also can calculate the current for this particular state, and here is the expression. So where I use this short notation here for E of H1 being this quantity in the parentheses, and EHH1 being all of this quantity. So yeah, so the first term it's known as being the current due to block function, block velocity contribution, and the second and third one it's the current due to the envelope function, envelope velocity. So now the results. The first result that I show here is for a topological quantum dot, which means that I have a thickness greater than the critical thickness of 3.3 nanometers. So here I have 4 nanometers, and the radius of my dot it's 50 nanometers. So as you can see, we obtain a discrete levels due to the 3D confinement. So now instead of that helicoid state, the bands of the helicoid state that go continuously in this, that continuously in K-space here, I just have these discrete levels in function of my JZ. So I also see that I have some states in the gap. That is basically the helicoid state I showed before for one interface. And I plot the wave function of them. And you can see that for this particular branch here, I have all of the wave functions localized near the interface, where here is the radial of our, the spatial position, spatial position of our dot. So we see that they are indeed the edge states. The state that lives here in the gap, they are really edge states. And more interesting, we show that the states, this helical edge state that merge in the valency band, they are not bulk band. They are not bulk. They do not. The literature shows that when you make one confinement or two confinements, so a strip, the edge states start losing their edge character when merging in this valence band. So here what we find is the opposite. So as much we increase our Z component of the total angular momentum, more and more the wave function will be localized near to the edge. So we use further. I will give the explanation for what we're seeing here. So. Exactly. Yeah, actually, it's okay. So basically, the geometry of my system, it's a cylindrical quantum dot. So it's precisely this picture here. 3 bands? Did you say 3 bands? No, it. Yes. So yeah. So no, it's a quantum dot. So I have confinement in z direction and also in the radius direction. Exactly. So this. Exactly. So the BT Hamiltonian, as Carlos said, it's the effective Hamiltonian of these two subbands. So I'm confining these two subbands in a cylindrical dot geometry. Exactly. So I have the BAT Hamiltonian plus this cylindrical confinement that imposes that the wave function for R greater than the radial of our disk, I have a zero wave function. So the wave function should vanish at this point. It's just that. Okay. So it's also possible to show that the current for a particular JZ with plus or minus has the opposite sign when I compare with opposite JZ and opposite spin. So which means that I still recovered the helicoid state in my system. Yeah, okay, so so this is the plot for this, for the spin up current. And so here I have the z direction, here I have the radial direction, and as we can see, the wave function, the current, it's localized near the interface, and more than that, they have opposite signs in each edge. So basically what we have, it's the current here, it's going out out of plane, out of plane in this sense. So it's positive z direction, and it circulates a bit, and when it comes back, it goes back with a negative sign. So basically, it's a circulating current like this picture here. So this is what is happening in this kind of quantum dot. So I have a spin up circulating current that it's doing this movement described by this picture. Sorry, described by this picture. And I have a spin down current that is going in the opposite direction. Okay, yeah, no source of drain. So yeah, it's just yeah. The J's that just can assume half integers. So it's plus or minus one half, plus or minus three half, plus or minus 50 half, just same half integers. Okay, so no, this is total angular momentum is integer, but this is the z component of the total angular momentum. Yeah, there are many states exactly. And here I'm just plotting this the lowest two. So this j basically it's minus one half, and this one it's minus three half. So as you can see, the density current increase as we increase the angular momentum. So then I will explain this later. How can we see that through a easy way? So now if I couple my quantum dot with a source with a drain, and with chemical potential of source and drain like that, it's possible to have transport through this dot without backscattering. So yes. So then what we think is, okay, let's start decreasing the thickness of our quantum dots, keeping the radius as fixed. So when I move from 4 nanometers to 3.3 nanometers, I see that my system is already in the trivial case where I observe here a time gap. And if I decrease even more for 2.5 nanometers, I observe a huge gap. So I really come back to the trivial regime without helical edge states in the gap. So if you guys pay attention in these two branches here, so seems that as I decrease the thickness, seems that those two branches were pushed up to the conduction band. So seems that the helical edge states that I had here, seems that they were just moved up to the conduction band. So here we make the question, are they still helical edge states? And actually the answer is yes, they still helical edge states. However, due to the many energy levels here, now I can have backscattering. So I still have in these two branches that are edge states, but now I cannot have transport without backscattering. Exactly. Till now, I just call them edge state. So now what we thought it's, okay, so let's decrease the radius of our dot. Because once I do that, the energy the energy separation, the energy quantization between these two levels will be larger. So then I can move all of these states here in the middle to up. So for a trivial quantum dot with 2.5 nanometers of thickness and radius equal to 15 nanometers, I already can find three states that does not, separated state that does not contain any kind of discrete levels in between them. So here I plot the wave function of these three guys. And as you can see, with the exception of the lowest conduction state, all of the two other one, this one and this one, for instance, they are edge states. So I plot so through the current formula, I also can show that this guy here moves the current relate to this energy level, moves in opposite direction when I compare it to this one. So here I still have the helical edge state character. Okay, so I still have the helical edge state property. So here I plot again the wave function of my system, the current of these two particular level, and I regain again the same feature that I found in the previous one, the topological quantum dot. So okay, so here an important thing that it's if I again couple my system to a source and a drain with chemical potentials given by these two guys, it's also impossible to have backscattering. So here, even being our quantum dot in the trivial regime, I still find helical edge state that propagated in opposite direction, and I still have protection by time reversal against elastic backscattering. So here I have the same feature in both topological and trivial quantum dot. So I can have the same properties as we have in the topological quantum dot, but now for trivial quantum dot, which is surprising. So exactly, yeah. Now I will move to the explanation about this feature. So how can it be possible to have this kind of things? So so it's possible to obtain a centrifugal potential or a centrifugal force from the BHC Hamiltonian. So for the lowest, so once you're talking about just the lowest conduction band and also this energy separation, it's huge. We can just neglect for practice the term due it to the valence band. So the centrifugal potential for Jz equals minus 1/2, it's 0. So here I'm plotting the centrifugal potential. Here is the formula for the centrifugal potential. When I plug in Jz equals minus 1/2 for the spin up, that is the upper sign here, this guy will be 0. So the cylindrical potential and for z component of the total angular momentum, it's 0. So I observe an extended state. So there is no confinement. And this is what we do observe here when we plot the total wave function. So there is no confinement. However, when I move to this state, that is minus 3/2, now this guy it's not equals to 0 anymore. And so I have a potential like this. So okay, so I should mention that in order to have a potential like this, where the probability to find an electron will be where we have a small potential, it's just true when I have all of these two terms, so minus d plus b greater than 0. If I have minus d plus b less than 0, this potential here will have this form. So it will decrease, it will be minus infinite for r equals to 0, and will increase, and goes to 0 when I have my r tending to infinite. So, and this clearly this potential will have some preference, will have some confinement near the origin. However, when I have this minus d plus b greater than 0, the confinement of my wave function will be near to the radius of my disk. So here we can see that what is really pushing the trivial conduction levels of my dot is really the centrifugal potential. So it's really pushing the electrons to the edge. So if I increase even more the centrifugal potential, that by going to the next level, that is minus 50 I obtain an even more larger potential, which makes my wave function more and more localized. Yeah, please. Okay. Yeah. No, but here I'm not changing anything. What What do you mean by non-symmetrics? Okay, if you preserve time reversal symmetry, it's impossible to scatter from one helicoid state to the other one. No, if okay, you can do that, but there is some constraint in the potential. So you need a potential that is magnetic in the sense that it does not commute with time reversal symmetry. If you okay, so there is a paper PRL from 2006. No. Okay, no, 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 no. For one interface, you can. So basically, this is the scattering element. So if this scattering potential commutes with time reversal symmetry, you directly show that this guy is zero. Okay, so what we see here is that the centrifugal potential is really pushing the electrons through the edge. And an important ingredient to observe this, it's really the parameters here. So we need to have minus d plus b greater than 0. So if you do not have that, we do not recover these helicoid states pushed to the edge. So, okay, I just make comments about that. Okay, so as I said, we have the same filter in the trivial quantum dot and the topological quantum dot. So now we can ask, is there any kind of difference here? So the first thing that we analyze is the current. So let's try to compare the current of both of them. So to do that, we fix the same radius for the two quantum dots. On the left, I still have the topological quantum dot with thickness of 4 nanometers. And on the right, I have the trivial quantum dot with thickness equal to 2.5 nanometers. So here I plot the current due to the two first two lowest conduction states. And as you can see, I found a higher peak on the trivial quantum dot. So this is not surprise once the trivial quantum dot has a thickness smaller than the thickness of our topological quantum dot. Because to have a topological quantum dot, we needed a thickness greater than 3.3 nanometers. So in this case, the current will spread a bit. So the peak So then we find a higher peak and small nanostructures. So, however, if we integrated the current through half of the cross-section of our quantum dot, we obtain around 0.12 microampere for all of these guys, up to 0.5% of difference. So basically, till now, there is no difference between our topological quantum dot and our trivial quantum dot in terms of current, helicoid states, and protection. So basically, this is what we have done till now. So now we have already some calculations that is up to finished. So, and in these calculations, we will try to analyze the conductance of this dot when you couple them to two different leads, including some inelastic scattering. So we will do this by Green's function, and we will obtain a linear response in the beginning. So
Oh, I think I'm a bit confused.
go ahead.
I can see a difference between the topological and the trivial one.
Yeah.
Just by looking at the plot.
At the gap, right?
Sorry?
The gap. Here, there's a gap.
Yeah, there is a gap.
Yeah.
And I can understand what you did, that the states live on the edges, but there should be some significant difference between these two. And you just showed that the current is practically the same.
Exactly. So,
So
why you should expect some huge difference between these two?
Well, my point is here you have you have the edge states connecting the conduction and the valence band, and not in this case.
No. Exactly. But so I mean, okay, you are right. But what does this mean?
Well, I'm asking the question. I want to know what the difference is.
No, actually, there is no difference. This is the point of this work. So if you can tune the chemical potential like this guy, you will find the same filter. So it does not depend. I mean, you can still have helicoid state protect against electric backscattering, even being in the trivial quantum dot. We're not saying that this is topological. No, we know that this is not topological. We know that there is a gap, a huge gap here.
Yeah, exactly.
However, we can have the same filter in the trivial quantum dot.
So do you think it depends on the material? What if
Yes,
I-
as I said, in order to have this confinement here, okay, let me just come back one. Okay, so in order to have a localized trivial helicoid states, I do need a centrifugal potential like this one, which means that I need this BHC effective parameters greater than 0. If I have minus D plus B greater than 0, then I will have a centrifugal potential like this, and as a consequence, I observe some wave function near to my radius.
Yeah,
So-
that I understand. I'm just asking whether I had like gallium arsenide.
Yeah, so I
Could
didn't.
I have something like that?
So I will show a next slide where
No, I know.
Yeah.
That's why I don't.
Okay,
Well,
s-
it's surprising, but it's not that surprising.
Yeah, because it's mercury telluride. Yeah, so actually,
that's why
this
I'm
was
asking.
exactly the same question that we did. So then the next result that I will show here, it's for indium antimonide. So if you take indium antimonide and we apply some piezoelectric strain, I can find a crossing on the subbands, which characterize a topological insulator. So the same deal as the mercury telluride, and we still can find the same filter that we found in the mercury telluride. So it's not a peculiarity from mercury telluride. So it's it's kind of actually obviously depends on how do I mean depends on the value of your BT effective parameters. However,
Okay, but here you are also finding that indium antimonide that's in some range is topological.
exactly, but
Okay.
exactly,
So
yeah,
you'd probably find the same features.
yeah.
Okay.
However,
Okay. Yeah. Fine.
yeah. However, if you okay, so this is a BXL strain of 2.5%. However, if I put like 1%, okay, so I obtain basically I obtain the subbands, so they do not cross each other. So they tend like this, okay? So if I take the critical thickness, okay, so no, not the critical, but if I work in a critical in a thickness around this point, I still can recover this the filter here that I have helical edge states living near to the edge, protected against electric backscattering, even having a non-topological material. So it really does not depend on the on the potential to be topological. No, you don't need crossing. As I said here, I don't have a crossing, but I still can find this filter.
I would say this TI thing is always overrated a little bit. You know, to have edge states, especially in a cylindrical geometry, is natural. You just, you know, the electrons are circulating like that. They tend to be near the edges, and you're protected by just the geometry. So you essentially emulate.
No, actually, I mean,
essentially
it's not.
emulate the
It's not
protection.
just. Yeah. Okay, but. Yeah, but so okay.
Why don't we do this?
Yeah.
Why not?
For
Well, that's
okay,
fine.
so for Alaska, for
Why
Alaska.
don't you? Why?
So why do you think that you cannot be like that? No, come
Oh.
on. Quantum mechanics does
Quantum
not
mechanics
abide.
then is all wrong.
Yeah.
Because it contradicts common sense. Why don't we just let Dennis finish the
Yeah.
Green's function part, and then we come back to the discussion?
Okay, so but
Yeah.
I should mention
Yeah, go on.
an important point here that we do need to have a constraint in these parameters. So if I don't have a constraint, so no, it is not. No, it's just no, it's just okay. So the BHC model is just an effective model that describes two subbands. It's an effective model that describes two subbands. So the M parameter that is inside the BHC could be greater than 0, which means that you are in the trivial regime, or it could be less than 0, which means that you are in the topological regime. So the BHC model does not say anything about topology if you don't have a mass less than 0. So it's just yeah, it's the gap. Yeah. So BHC model is just an effective model that describes two subbands. So I need this relation. If I don't have this relation, then my potential will be like that.
All right, Dennis, I think we should move on to the
Okay.
last part so we can wrap up. Then we can discuss in the discussion.
Okay, so okay, so the point now we are okay. So as I said, we already have showed that this filter here also appears in indium antimonide quantum dot with piezoelectric strain. And further, we will analyze the conductance using Green's function in linear response to see that if the conduction will stay the same. If you increase in elastic scattering, we want to analyze what things will, I mean, with difference, if there will be a difference, will appear here. So till now we just analyze the current and say, and we conclude that the current is the same for trivial topological. Yeah, yes, yeah. Yeah. Yeah, this is the further calculation. I cannot say anything until now. No, not wrong feeling. Why do you expect?
Well, it's still linear response, right? So you calculate the Green's functions for the conductance using the eigenstates and eigenenergies of the system without the leads, right? So that's what we do.
So the coupling. Okay, so there is a gamma left, a gamma drain, and a gamma source. No, it's just microscopically. We just couple. Okay, so basically the conductance form that we are using in linear response, we have gamma L, gamma R, gamma L plus gamma R, where this gamma L and gamma right, it's given by this. So basically we have some macroscopic text. No, actually here, okay, we didn't make any kind of assumption in the. Okay, oh. Yeah, in principle, we can use some spin dependence in this guy, but I mean, I cannot see how does it. You can, I mean, yeah. And here the imaginary. So this is our further task. It's calculate the conductance through this formula in linear response and see if we can obtain some difference in the conductance between the topological and the trivial regime. Yeah. Okay, yeah, so thank you.
Questions? Comments?